The electrolyte in between should support only the working ion conductivity or serve as a medium for the transport of, in this case, lithium ion, because we are talking about lithium ion batteries during the charge discharge process, as you see here. Currently, in your cell phone, laptop, and electric vehicle, we use a carbon anode, graphite anode. The cathode started with lithium cobalt oxide in the 1990s. Now the trend has been slowly to replace cobalt with equal amounts of nickel and manganese to reduce costs. So that's what the technology we have. So even though it looks very simple, from a chemistry and physics point of view, it's very complicated. So I put here the energy levels of the anode and cathode. And then in between you have the electrolyte. This is the highest occupied molecular orbital of the electrolyte. This is the lowest unoccupied molecular orbital of the electrolyte. So these two redox energies, anode and cathode, they have to lie within this band gap of the electrolyte. Otherwise, what will happen is, supposing if this is below the anode energy level, when you charge it, we remove electron as you see here. That electron has to go here and fill here. If this is lower than this, somewhere here, then when we charge, the electron will go and into the lowest unoccupied molecular orbital of electrolyte. That means electrolyte is getting reduced. So during this operation, electrolyte should not undergo any oxidation or reduction, or in other words, should not undergo any acceptance of electron or removal of electron. So that's why these two have to be within the band gap. On the other hand, if the cathode level is below the HOMO, then during charge, instead of removing the electron from the cathode, we will be removing the electron from the electrolyte. So that means I'm oxidizing the electrolyte. So that's not good. It's very complicated. The voltage is determined by the energy difference between the anode and cathode. That is this. That means you have to keep the cathode energy level as low as possible, anode energy as high as possible, but it is thermodynamically limited by the energy levels of the electrolyte. So you cannot stay outside that. If you are, then you will have unwanted oxidation reduction. So the energy density used at time is the voltage you get. That's the difference in energy between these two electrodes times the amount of charge you can store in these materials per unit volume or per unit weight. So that's what the energy density is. Now during usage or during charge, you pump the electron from the lower energy to a higher energy using electricity. When you talk or when you use your laptop or when you drive your car, the electron will spontaneously fall from this higher energy to the lower energy. There is a free energy change, and that is taken out as electricity. N is the number of electrons involved, F is the Faraday constant, E is the voltage. Now, why are we all concentrating on the lithium ion? Is that the only battery technology available? No, there are a lot of other technologies available. Lead acid. Each one of our car has a lead acid battery. There was nickel cadmium, nickel metal hydride. They have slightly higher energy density than lead acid. Before lithium ion batteries were commercialized, these were the ones we were trying to use in laptop or cell phone, kind of. But these use water-based electrolytes. For example, lead acid use sulfuric acid, nickel cadmium and nickel metal hydride, they use potassium hydroxide. So they have water-based electrolytes. So that means the window will be smaller than what I have shown you here. Therefore, this will be lower, that will be higher. So the cell voltage will be largely less than 2 volt. In the case of lithium ion, we use non-aqueous water-free solvent. Therefore, this window is wider. So we get 4 volt battery instead of a 2 volt battery. So you can see here instead of 2, we have 4. So user time or energy density is at least doubled. And if you store more charge, it can also be even increased much more. That's why all the action is now on lithium ion for all these applications. Okay. Now, as we move forward, it's great. We have lithium ion. So when you have batteries, there are few things we have to worry about. At least 6 parameters, as I have shown you here: cost, power density, energy density, cycle life, safety, and environmental impact. They are all intimately linked to the materials. Which material we use, that's what they determine. Among these 6 parameters, cost is one of the most important parameters. Cost is not raw material cost alone. If the battery is more safe, I do not have to worry about lawsuits. And then if it is cycling for a long time, I do not have to replace. If it stores more energy, I can make less number of cells. So everything contributes to cost. So cost is the biggest driver right now. In addition to that, you don't want to make low cost batteries and blow up. So safety is another important parameter. Again, materials determine the safety, the materials we use, plus cell design. How do we manage the batteries or battery management system, and how do we use it? Are we abusing it? All those will also contribute to safety. So as we move forward, cost is a major issue, and safety is another issue. My talk is kind of going to be focused around this. So when I say cost, in the battery, we use a lot of different stuff, as you see here. In the overall battery, 75% is materials cost. In that, 75% is the cathode cost, that is the positive electrode cost. And the positive electrodes also determine the cell voltage and the cell energy density. So that's why a lot of action, lot of work is on cathodes, because the 50% of the cost is coming from cathode. If you think of cathode, you can see cobalt is, you can see the price as well as concentration or abundance. Abundance is low here. When you move from right to left, abundance is increasing. Commercialization started with lithium cobalt oxide initially. So that's a higher cost, less abundant. Right now, cobalt is almost gone. We are working around nickel. But down the road, that nickel could also be a problem. So we have to go with manganese or iron or even sulfur, for example. Sulfur is abundant and it is a byproduct waste in the petrochemical industry, gas companies, so we can use that. So that's slowly we have to come from the top right corner to the bottom left corner. That's what we need to see. I did not put sulfur here, but I'll show in the next slide. So that's what we are dealing with. So how did it all happen? Everything we use now, they were all not developed yesterday. They were all developed in the 1980s. Particularly, I showed you cathode is the most dominant cost and energy density. They were all developed by Professor John Goodenough group, both at the University of Oxford and at the University of Texas at Austin, 1980. And also, it involved 3 visiting scientists, or kind of visiting scientists slash postdoc from 3 different parts of the world. Mishishima had a job in Japan, came as a visiting scientist, worked with John Goodenough. They developed lithium cobalt oxide. He left. Michael Thackeray came from South Africa. He worked on lithium manganese oxide spinel. He left. I came from India after doing my PhD. So I started working on as a postdoc or visiting scientist on iron containing polyanion compounds. So that's where inductive effect was invented. So all of them are, I came after these 2 guys up. So we did not have any overlap. So all the cathodes technology we use, they're all based on this basic concept. Right now, layered oxide is heavily used, but because of the cost, there is more interest to go towards these kind of compounds, or lithium iron phosphate, LiFePO4, that belongs to the same kind of polyanion. Now, we worry about a lot about cost and safety. This is more expensive. This is less expensive. This is iron containing materials are the least expensive as far as metal oxide based cathodes. Iron is the cheapest. You know, steel. Everywhere you see, cheapest, abundant. one of the most abundant element. Also, this will release oxygen, more safety issues. Lithium manganese oxide is better. Here the polyanion sulfate or phosphate, they hold the oxygen very tightly, so they don't lose oxygen when you overcharge or during operation. So safety-wise, this is also better. So they're all already built in the 1980s. Everything we use right now, commercial, is based on these three or these two families of cathode. Right now, this is out because it has a lot of cyclability issues. So at least to tell you, anything you develop will take 20, 30 years before you put it in the device or put it in the market. Now, I talked about cost. You see, lithium and cobalt, this is abundance. Low abundance means higher cost. So we have to get rid of them as we move forward if we can. So like I said, cobalt is kind of replaced with nickel. That's okay. This means better than these blue. The green ones are the ones we should be focusing as we move forward. For example, sulfur, manganese, sodium, iron, aluminum, silicon. So that's where we need to give you an idea. So in my group, everything we do is focused towards this aspect. How do we continuously go towards making the cost lower and making the technology sustainable and avoid supply chain problems? So right now, cobalt-free lithium-ion batteries, we have eliminated cobalt in that layered oxide. You can have high nickel with a little bit of cobalt or almost no cobalt. We have been successful. And we have a startup out of my lab. They are in Houston. They are scaling up. The next is, I say cobalt is a problem today. Nickel is a problem tomorrow. Lithium will be a problem day after tomorrow. So what do we do? So this is the roadmap. No cobalt and no nickel. Then you go to the polyanion cathodes I was showing, iron-based lithium iron phosphate or other iron-based cathodes. Then finally, can we eliminate lithium? Yes. Then you go to sodium ion. Sodium ion, there is no lithium here. Sodium is the working ion. Sodium is abundant, plenty in the ocean. So we do not have supply chain problem. And then sodium cathodes can also be made with iron and manganese almost, or with a little bit of nickel with them. No transition metal, but you still can have lithium, that is lithium-sulfur. Finally, no mined metal at all, that is sodium-sulfur. Sodium is plenty in the ocean. Sulfur is in the petrochemical industry. You do not have to mine. So that's a dream technology as far as I am concerned, or sodium organic. Cost will be very low, sustainable, and there will not be any supply chain problem. You do not have to mine, for example, cobalt mining in Central Africa, Democratic Republic of Congo, lot of child labor, lot of ethical concerns, and different countries go and purchase the mines, so it can become a nightmare. So we have to focus from left to right as we move forward. So this is what we are doing in my lab. Work is happening all the way from left to right, excepting the organic, we don't do much now, but it's going all the way from right to left up to sodium sulfur. With that, the time is short, so I'm going to tell you a few examples. Okay, this is fine. Do we have some results we can see, so that we can see, yes, it can become potentially possible? So I'm going to show you some results. First, elimination of cobalt. So this is called lithium, nickel, manganese, cobalt oxide, NMC cathode. That's what we use in the laptop, cell phone, in the electric vehicle. The question is, the whole commercialization started with complete cobalt here, one cobalt here. The tendency has been to replace cobalt with nickel and manganese because to reduce cost and increase energy density. There are several factors. These three elements have pros and cons. They bring advantages or disadvantages. The first one is, if you look at the cobalt 3+, 4+ redox band, that is overlapping with the top of the oxygen 2p. So if you charge more than 50%, then oxygen will be released. So the capacity we can use from lithium cobalt oxide is only 50% of its theoretical capacity. Because if you use more than 50%, you will remove electron from the oxygen band. So oxygen oxide ion will be oxidized to oxygen gas. So that's a safety problem. So we can't use it. If you take manganese, it's well above oxygen 2p. So you can go all the way to manganese 4 plus. You can, in principle, use the full capacity, but there is another problem. So from this first aspect, chemical stability point of view, cobalt is the worst, manganese is the best. The next aspect is when we charge, M has moved a little bit. So when we charge, we remove lithium from this layer. So the M from here can migrate from this layer to that layer via a neighboring tetrahedral site. Here it is in the octahedral site. It may tend to move to this six-fold octahedral site, but when it moves, it cannot directly jump. It has to go through an intermediate tetrahedral site, as you see here, through an intermediate tetrahedral site. So that means if this ion does not like tetrahedral site, then it won't move. So one can calculate the difference in octahedral site or crystal field stabilization energy in the octahedral site and crystal field stabilization energy in the tetrahedral site. If you take the difference, that tells you to what extent each one of these ions are stable in the octahedral site. For example, cobalt loves octahedral site, weak stabilization, negative quantity. It doesn't want to move from this layer to a neighboring tetrahedral site to the lithium layer. It does not transform from layered to a spinel-like phase. So that's good. That's a gift with lithium cobalt oxide. Manganese, if you take very small difference, so manganese will tend to move from that layer through this tetrahedral site to this layer. So if you have manganese-rich compounds, you will have voltage decay because when it transforms from layered structure to something called spinel structure, lower voltage, so there will be a continuous voltage decay. So that's not good. So that I call it as structural stability. For that, manganese is not good, cobalt is better. You see on the top, you have for one of them, manganese is good, for the other one, cobalt is good. So there is a problem there. If you take nickel, there are a lot of other criteria you can look at here. If you take nickel, nickel is kind of in between cobalt and manganese in all of this. And nickel band is also only barely touching the top of the oxygen 2p. So you can oxidize nickel all the way to 4 plus. So you can get higher energy density as compared to cobalt. So that's why cost is lower, higher energy density. That's why all the action is higher and higher nickel compound, lower cobalt or no cobalt. But now that doesn't come with an easy task. As I said, higher nickel, higher capacity, lower cost, good, but they suffer from severe bulk and surface degradation, cycle instability. You see here lower nickel content. If you go to higher nickel content, you get higher charge storage capacity, but it is behaving bad. You cannot charge discharge for large number of cycles. Not only that, when you increase the nickel, they are also becoming thermally less stable when you increase the nickel content. So that will lead to safety problem. Not only that, the nickel 3 plus is not very stable. So if you manufacture the material and keep it in air, they will form lithium hydroxide and lithium carbonate on the surface. That is called in the industry as residual lithium. You see here, this is 33% nickel, 50% nickel, 70% nickel, 90% nickel, 100% nickel. The residual lithium quantity is exponentially increasing when you go to much higher nickel content. So that's a headache. If you have the surface hydroxide, lithium carbonate, when the companies like Samsung or Tesla makes electrodes, it will clog. They cannot make good electrodes. So it's not, it doesn't work. So that is a problem. So we have cycle, thermal, and air instability. Why nickel has this problem? Is very basic chemistry. If you take manganese, we have binary oxides all the way up to MnO2. So manganese is very stable, 2+, 3+, and 4+. Cobalt, you have up to CO2, O3, but we do not have any COO2. Nickel, only NiO is known. None of these are known. So nickel 3+ is not stable. Nickel 4+ is not stable. That's why we have this problem. So the job in my lab is how do we overcome these difficulties? Both by making cathodes with more surface robust or less reactive cathode surface and more less reactive, more robust electrolyte. That's what we do. So I'll quickly go over with one example here, for example. So we make our own material using a tank reactor. We buy only the raw material. So that's what we do. We make 12 micron secondary particle, as you see here. Any composition we can make. I show you a bunch of compositions here. Everything has nickel around 90%. That's why you see 90, the first number. The NMA means there is no cobalt, only 5% aluminum and 5% manganese, and then 90% nickel. That performance here, the gray curve here, is NMA. Gray curve here is as good as some of the cobalt containing material. The answer here is, our conclusion here is, cobalt is no longer necessary. Cobalt is gotten rid of because you get better cycle life as nickel cobalt containing materials. And this is what my startup in Houston is working on, to scale up NMA with various nickel contents without any cobalt. This is another example to show surface reactivity is the major issue. We made the material, for example, by two means. In one, we co-precipitated nickel, cobalt, and aluminum. In that case, aluminum is distributed throughout the bulk, surface as well as bulk, that we call it as BNCA. In another case, nickel and cobalt is co-precipitated first, hydroxide. Then you add aluminum oxide, then you heat it. During that process, aluminum will be preferentially present a little bit more on the surface. So that means this cathode, even though same overall composition, this cathode will have more aluminum on the surface, and that will be less reactive with the electrolyte. That's why you see this material cycle, same color code. The red one cycles much better, as you see here, than the blue one. That is, aluminum is not very much on the surface. So if you stabilize the cathode surface, you reduce the surface reactivity with the electrolyte, so they cycle better. Next is elimination of cobalt and nickel. There, the lithium iron phosphate, for example, 3.6 volt, very flat. There is no cobalt, no nickel. This is lithium manganese iron phosphate. The manganese redox is at 4 volt. Iron redox is at 3.4 volt. So you have a break. So you can make with 60% manganese in this material or 70% manganese in that material. You see those two curves. More importantly, but the energy density will be lower, lower operating voltage. So what we have been doing is take this material, that's this 50% here, and then blend it with this layered oxide having high nickel. So by the time you blend it in this blend cathode having two materials, the overall nickel content will be around 50% or much way down. Then rest is manganese and iron. You see very nice voltage profile when you blend this and this, very nice voltage profile, this profile. Whereas if you take only this, then you have a step. So when you blend this, that voltage and this voltage, they kind of mixed together, and at some voltage, one of them operate more, the other. It's a very, very nice voltage profile. Companies don't like break in the voltage profile, like you see here, break. No, this is very much more smoother. So that's good. This has a lot of potential. Cost is reduced compared to the previous ones. Next is elimination of, how much time is that? Okay, almost. Elimination of cobalt, nickel, and lithium. So that is sodium ion cell. Again here, electrolyte is the major issue. So this is a sodium compound, very little nickel. As you see here, there is no lithium. We have developed a new electrolyte with trimethyl phosphate and sodium nitrate that gives day and night difference compared to the conventional electrolyte. Not only that, they also give better safety. This conventional electrolyte, this is our electrolyte, does catch fire. The other does not dendrite. This electrolyte, the electrolyte again plays a dominant role, gives better safety, better cycle life, as you saw here. So better cycle life and better safety. Next is the elimination of elimination of mined metal excepting lithium. So that is lithium-sulfur. You see huge charge storage, 10 times more than the oxides I already talked about. But when you have sulfur, it forms intermediate polysulfides that goes back and forth between the two electrodes, messing up. That's a problem. Sulfur is a poor electronic conductor, poor ionic conductor. You remember in the first slide I showed you, the electrode should support both ionic conductivity and electronic conductivity. Sulfur is bad for that. If you use sulfur, then you have to take lithium metal, so it is a problem. So there are a lot of challenges. Nobody is able to get more than 300 cycles in any reasonable cells. That's a problem. So now, using chemistry, you see sulfur, selenium, tellurium, they're all in the same group. But tellurium behaves very different than sulfur or selenium. It's more towards metallic. So when you add small amount of tellurium, you see the cycle life can be changed drastically, because when you add tellurium, it forms Li2TS3 on the anode surface. That leads to smooth deposition of smooth plating and stripping of lithium on the anode. That's why it gives better cyclability. So chemistry plays a bigger role. How you can employ the chemistry to overcome some of the problems. Final elimination of mined metals, that is sodium-sulfur cells. That's a TREAM technology. Again, electrolyte is the major problem. If you use conventional electrolyte, lot of over voltage, they produce gas. They also form dendrites. We have developed a localized high concentration electrolyte that has very low over potential, no gas evolution, and dendrite formation is suppressed. And the performance is shown here, around 800 or some capacity with these sodium-sulfur cells. Voltage is lower, but you get huge capacity, but the cost is very, very low, abundant sodium-sulfur. And then we have done a lot of characterization. When you change the voltage, electrolyte, initially it forms polysulfide. Then after 1 or 2 cycles, you don't see any polysulfides. The reaction mechanism changes from a dissolution precipitation reaction to a quasi-solid state reaction. That's why it performs much better. So it's a conclusion. So fundamental solid state inorganic chemistry has led to the commercialization of lithium-ion batteries over the years. Moving forward, cost, sustainability, supply chain will be the major challenge. So progressively, we will eliminate cobalt, nickel, lithium, and any mined metal. If it is, that will be sodium sulfur or sodium organic. So near term, you will have cobalt-free, high nickel layered oxide cathodes I talked about. Next, cobalt-free and nickel-free polyanion like lithium iron phosphate or lithium iron manganese phosphate or other polyanion cathodes. Mid-term, cobalt-free and nickel-free sodium ion or lithium sulfur batteries. They have challenges. I think before lithium sulfur, maybe sodium ion with this may come first, and then this may come. Finally, no mined metal, that is sodium sulfur and sodium organic. That is the long term. These could also be a little bit long term. So when I say near term, mid term, long term, it's kind of how do we progress, some kind of a scale, but there may be some overlap. So this is my current group. I'm very grateful to all the students and postdocs who have worked with me over the years. This is my current group. And then I'm also grateful to the funding agencies, particularly the US Department of Energy, Basic Energy Science, as well as the Vehicle Technologies Office, NSF, Army, Welch Foundation, and the company CBMM. Thank you very much. I'll be happy to answer.